All right, let's get right into it. Today, we're going to pull back the curtain on one of the coolest and, honestly, most important ideas in all of computer science, the binary tree. You may not have heard of it, but it is the secret engine running behind the scenes of your digital life.
I mean, have you ever really thought about that? You go to a website, you type in your username, and bam, your profile just appears. Instantly, out of millions, maybe billions of users. How? Well, I promise you, it's not magic. It is an incredibly clever way of organizing information, and that's what we're here to figure out today.
But, before we can appreciate the solution, we've got to understand the problem. So why isn't the most obvious way to organize things, just putting them in a simple list, good enough?
Well, think about it. On the one hand, you could have total chaos, just a jumbled mess of data, kind of like a stack of dirty plates. Not useful. So, okay, what if we line everything up nice and neat, like people waiting for a bus? That seems organized, right? Sure. But what if you need to find someone in the middle of that line? You've got to ask every single person, one by one, from the very front. And what if a new person needs to squeeze into the middle? The whole line has to move. It's organized, yeah, but it's super rigid.
And that's the real issue here. Going one by one through a huge line is just painfully slow. And trying to change things in the middle, it is a massive headache. When you start talking about millions or billions of items, this whole line idea just completely falls apart. There has to be a better way.
So if a straight line is the problem, what's the solution? Well, we need a totally new shape. We have to stop thinking in lines and start thinking in hierarchies. We need to think in trees.
And here's the cool part. You already do this every single day. Anytime you're clicking through folders on your computer, you are navigating a tree. Your main drive is like the trunk, the folders are the branches, and all your files, they're the leaves.
You could even see this idea in your own family history, right? A family tree is a perfect natural example of this kind of top-down structure.
And of course, you see it in basically any company. The classic org chart, CEO at the top, departments branching out below. That's a tree structure, plain and simple.
Okay, so let's get just a little bit formal for a second. In computer science, a tree is just a way to model a hierarchy. You've got one single starting point at the top, we call that the root, and then everything else branches out from there into smaller and smaller subtrees.
Let's just use that org chart to nail down the lingo. The person at the very top, the CEO, that's our root. The people at the very bottom who don't manage anyone, those are the leaf nodes. And pretty much everyone in the middle, like the VPs, we call them internal nodes because they have a boss above them and they have people reporting to them below. Simple, right?
Now, these general trees are super useful. But in the world of computers, we can make them even more powerful by adding one tiny little rule. So it is time to meet the star of our show, the binary tree.
And the rule is so simple it's almost funny. Binary just means 2. In a binary tree, every single parent can have at most 2 children, a left one and a right one. That's it. That's the whole rule. And that one simple restriction is what makes everything else possible.
But just having 2 children is only half the story. That gives us a structure. To turn it into a super fast search machine, we need to add one more organizing principle. This is the secret sauce.
And here it is. This is the golden rule of what we call a binary search tree. For any spot you're standing on in the tree, everything to the left is smaller, and everything to the right is bigger. This one simple idea organizes the entire tree for ridiculously fast searching. All right, let's see it in action. Talk is cheap. Here is a binary search tree. Our mission, should we choose to accept it, is to find the number 24. How do we do it?
Okay, so we always start at the top, at the root. In this case, that's 29. And we ask one simple question. Is the number we're looking for, 24, smaller or bigger than 29? Well, it's smaller. So because of our rule, we know it has to be on the left side. And just like that, poof, we've just ignored the entire right half of the tree. Gone.
So now we're at 14. We do the exact same thing. Is 24 smaller or bigger than 14? It's bigger, so we follow the rule and we go to the right. And again, we've just chopped off another whole section of the tree we don't need to look at.
And on our third jump, we land right on 24. Done. We found it. Now, stop and think about what just happened. We found our number in just 3 tries. 3! If this were a simple list, it could have taken way longer. But get this. If this tree had 1 million items in it, searching one by one could take 1 million steps. But with this method, it would take about 20. That is the insane power of cutting the problem in half over and over again.
Okay, so searching is crazy fast. I get it. But what about when things change?
What happens when you need to add new data? Or worse, remove old data? How does the tree keep that perfect left is less, right is more order? Well, adding things is pretty straightforward. You just search for where it should be and plug it in. Removing things is a little trickier, especially if the node you want to remove has 2 kids. You can't just leave a hole, right? So the trick is to find its replacement. You go to its right-hand side and find the smallest value over there. Then you pluck that value out, drop it into the spot you're trying to delete, and now the tree's order is preserved. It's a clever little swap that keeps everything tight.
Here, you can see it right here. We want to get rid of the number 30. The algorithm looks to its right, finds 40 as the next smallest thing, and it swaps 40 into 30's old spot. And just like that, the whole structure is valid again, perfectly ordered and ready to be searched in a flash. So let's bring this all home. Why are we going through all this trouble? All this talk about roots and leaves and left and right children? Why does any of this really matter?
Well, here's the final and most important piece of the puzzle. It's all about the tree's shape. If your tree is nice and bushy and balanced, like the one on the left, it's going to be blazingly fast. But if you're not careful, you can end up with a tree that's long and stringy and unbalanced, like the one on the right. And what does that look like? Yeah, it's just a slow, crooked line. So the real secret isn't just using a tree, it's keeping that tree balanced.
So if you take one thing away from this, let it be this. The way we structure our data isn't just about being neat and tidy. It's about speed. It's the fundamental difference between something being instant and something being impossible. The right structure is everything. And it really makes you wonder, doesn't it? What other parts of your digital life that feel like magic are really just a simple, elegant tree working perfectly in the background?